We are diving straight in today with a really fascinating piece of engineering from Apple. It's called STARFlow-V.
Yep, end-to-end video generative modeling with normalizing flows.
And this paper is a big deal because, it's really the first strong evidence we've seen that normalizing flows, or NFs, can produce high-quality video.
And not just that, but video that's genuinely competitive with, the diffusion models that are everywhere right now.
Exactly.
And it's not just about hitting the same quality bar. The real story here is the architectural approach. NFs are likelihood-based, they're trained end-to-end, and they give you exact likelihoods.
And crucially, they support causal prediction.
That's the key. For anything like robotics or real-time world models, causality is everything. And STARFlow-V does it without the usual traps you see in autoregressive diffusion.
So how did they crack it? Because NFs have always struggled with scaling to something as complex as video.
Well, it really comes down to two big innovations in the architecture. First is what they call a global local latent space. It's how they manage the spatiotemporal complexity. And second, a really clever sampling method called blockwise Jacobi iteration. This gives them something like a 15 times speed up at inference.
Which is what makes this whole thing feasible in the first place.
Right. It takes NFs from a theoretical curiosity to a practical tool for video.
That's a great summary. It really gets to the heart of why this paper is so exciting. We've seen generative modeling just explode.
Oh, absolutely.
But video is still, the final frontier. It's just so tough to get that spatiotemporal structure right and to make it robust over long periods. And so far, diffusion models like the ones in Sora or VO3, they've been the champs.
They have. They dominate when you can just generate a whole chunk of video in one go. That's their sweet spot, the non-causal approach.
But that's not what you need for interactive systems.
No. Once you start talking about robotics or a real-time simulator, diffusion hits some pretty fundamental walls.
So what are those specific pain points that STARFlow-V is really designed to fix?
Okay, so the first is just how they're trained. A diffusion model learns to reverse a noise process. You add noise to a frame, and you train the model to remove it.
Which is very computationally expensive for video.
Very. And more importantly, you're not optimizing the exact likelihood of the data. You're optimizing a lower bound on it. It works, but it's not as principled as direct maximum likelihood.
And the second issue is the big one, the reason we need autoregressive models at all.
The causality problem.
Right.
Precisely. If you want a model that can stream, that predicts frame, and using only the frames that came before it, a standard diffusion model just won't work.
So you can try to force it into an autoregressive structure, but then you hit this other problem.
You hit the wall of exposure bias.
Let's unpack that a bit, because it's so central to the argument here.
For sure. So think of it this way. When you're training an autoregressive model, you're feeding it perfect ground truth frames. It learns to predict the next frame based on a flawless history.
The ideal scenario.
Right. But then you go to use the model for inference. And what does it have to work with?
Its own predictions from the last step.
Which are never perfect.
Yeah.
There's always some tiny error, a little blur, a slight color shift. And that tiny error gets fed into the model to predict the next frame.
And the error from that frame gets fed into the next one.
And it just compounds. It snowballs.
Right.
Over a few seconds, your video just degrades into a blurry, distorted mess. That train test mismatch is the killer for AR diffusion.
So STARFlow-V's whole premise is that normalizing flows are the answer. They're invertible, you get exact likelihoods, non-iterative sampling, all these great properties. But the question has always been, how do you scale that to video?
And that's exactly the challenge they took on. The first step is just brutal data compression. You have to. They use a pre-trained 3D causal VAE to just shrink the problem down.
How much are we talking?
A lot. They compress the spatial dimensions by a factor of 16 and the temporal dimension by 4. The actual flow model works entirely in this much smaller 48-channel latent space.
Because trying to do it on raw pixels would just be impossible.
It's computationally intractable, yeah.
Okay, so once they're in that compressed space, how does the flow actually handle the sequence? This is where the global local architecture comes in, right?
Yes, and this is the really clever part. The model is split into two parts. A shallow stack, they call it FS, and a deep causal transformer flow, FD.
Okay.
I like to think of it like writing a novel.
Oh, I like that analogy. Go on.
The shallow stack, FS, is like your copy editor. It only cares about local, within-frame details.
Yeah.
It uses these alternating masks to do per-pixel refinement, making sure the image is sharp and clean. It's not worried about the plot.
And the deep flow, FD, that's the novelist, the big picture thinker.
Exactly. That's the brain of the operation. It handles the global long-range temporal context. It's what makes sure that a ball that's thrown in one frame is still moving in the next, that the story makes sense over time.
And splitting it up like this, it seems like that directly attacks the exposure bias problem we were just talking about.
It does. It's the key insight. AR diffusion propagates errors at the pixel level, the most complex, high-dimensional space. But STARFlow-V's deep flow conditions on the previously generated latents.
So not the pixels.
Not the pixels. And the latents are much simpler, much more robust to small errors. So by operating on these more stable representations, the model avoids that cascading failure mode you see in other systems.
You're not passing on errors in the most sensitive domain? That makes a lot of sense.
And because the whole thing is just a composition of invertible functions, it's still a true normalizing flow. You can train the whole system with exact maximum likelihood estimation, which is simpler and reduces that train test mismatch right from the start.
Okay, let's switch gears to another common problem with NS dot noise. You often have to add noise during training just to keep things stable, but then your samples come out a little bit noisy.
Right, you need a cleanup step.
Yeah.
And they tried a few of the standard ways of doing that. Well, they failed pretty badly for video. They tried fine-tuning the VAE decoder, but it just destroyed the temporal consistency. You can see in the paper the videos are blurry and jittery.
And just using the raw gradients from the flow, the score, that didn't work either.
No, for two big reasons. One, it created this weird high-frequency speckle noise. But two, and this is the deal breaker, the score is non-causal.
How so?
The gradient at a given frame, say frame n, actually depends on information from future frames. So using it for denoising would completely break the streamability of the whole system.
So to fix the noise and preserve causality, they came up with something new, flow score matching, or FSM.
Right. So instead of using that raw non-causal gradient, they train a separate, lightweight, causal neural network to act as a denoiser.
And they train it alongside the main flow.
Jointly. And the clever part is that they use the network's own inductive bias to smooth things out. That naturally suppresses all that high-frequency noise you get from the raw gradient.
So the network architecture itself is doing the smoothing work.
Exactly. And they enforce causality with a block causal mask, so the denoiser can only look at the current frame and maybe one frame ahead. It keeps everything strictly streamable, and they can train both parts together with almost no extra computational cost. It's a really elegant solution.
Which brings us to the elephant in the room for any normalizing flow discussion: speed. I mean, the model can be perfectly principled, but if it takes half an hour to make a 5-second clip, it's a non-starter.
That's the classic bottleneck. Sequential autoregressive sampling is just brutally slow.
So how did they get around that?
This is their other big contribution: blockwise Jacobi iteration. Basically, they reframe the problem of inverting the flow going from the latent noise back to the video as solving a fixed point equation.
And why does that help?
Because you can solve fixed point equations iteratively, and you can often parallelize those iterations. So instead of processing one tiny piece at a time, sequentially, they can group the sequence into blocks, and then they process everything within a block in parallel. The causality is maintained between the blocks, but inside them, it's all happening at once.
So you're trading, say, 100 tiny sequential steps for maybe 10 larger steps that are internally parallel.
That's the idea. And the performance gain is huge. They report about a 15x drop in latency compared to the standard way of doing it. It makes the whole architecture actually usable.
And they had another trick specifically for video to speed it up even more.
Yeah, video-aware initialization. It's really smart. It just leverages the fact that video frames are very similar to each other.
High temporal coherence.
Right. So when you start the Jacobi iteration for a new frame, instead of starting from a random point, you start from the solution you found for the previous frame.
Which should be really close to the new solution already.
Exactly. It means the algorithm converges in way fewer steps.
Yeah.
It's a simple idea, but it makes a massive difference in practice.
It seems like they squeezed performance out of every part of the pipeline. I saw a note about pipeline decoding, too.
That's another benefit of the global-local split. The deep flow, FD, is the bottleneck. But since it's separate from the shallow flow, you can have it just continuously churning out latents.
And then
you can have separate threads for the shallow flow, FS, that just pick up those latents and do the final refinement and denoising in parallel. It keeps the whole GPU busy.
So when you put it all together and look at the results, how does it stack up against those big AR diffusion models?
It's pretty stark. STARFlow-V is just way more robust to that exposure bias we talked about. The diffusion models start to blur, the colors drift, things start to deform over a few seconds.
Because of that compounding error.
Right. Whereas STARFlow-V stays sharp and temporally consistent for much, much longer.
And that long horizon stability is the key takeaway for me. They trained it on 5-second clips, but showed it generating 30 seconds of stable, coherent video.
Yeah, that's the proof in the pudding. It shows that conditioning on those robust latents is just a fundamentally better strategy for long-term causal generation.
And beyond just the quality, the fact that it's a normalizing flow gives it this incredible versatility, right? One model can handle a bunch of different tasks.
That's the magic of invertibility. For image to video, you don't need a special encoder. You just run the flow forward on the image.
And that initializes the whole system.
It populates the KV cache with the history it needs, and you're ready to generate. Same for video-to-video editing. You encode the source frames to fill the cache, and then you let it auto-regressively generate the edit based on your prompt.
It's a really unified architecture. But let's be fair, the authors were very upfront about the limitations. It's not perfect.
No, not yet. First off, latency. Even with the 15x speedup, it's still not real-time on a standard GPU. It's still a heavy model.
Okay.
Second, they haven't found clean scaling laws yet. That's a big deal for research because it means you can't reliably predict how much better the model will get if you just throw more data or compute at it.
And then there are my favorite failure cases, the physics problems.
The octopus.
The octopus going straight through the glass jar.
Yeah, or objects just popping into existence out of nowhere. Yeah. It's a great reminder that the model has learned what video looks like, but it hasn't learned the underlying physical rules of our world.
Not yet. So the next steps are pretty clear. Make it faster, figure out how to scale it, and train it on data that can teach it some basic physics.
That's the roadmap. But I think the larger implication here is what this says about the future of generative models.
Go on.
STARFlow-V proves that normalizing flows are a viable path to high-quality video. And they give you things that diffusion models really struggle with. Strict causality and exact likelihoods.
So if the end goal isn't just making cool-looking videos, but building robust, predictable world models for things like robotics or simulation, systems that actually have to obey the laws of cause and effect, what does that mean? Are we seeing the beginning of a shift? Does the long-term future of truly reliable AI depend more on the architectural integrity you get from flows than the sort of raw generative power of diffusion?